Hello, this is Professor Dan Kernler, and this is our last video for Calc 3. Today we're going to talk about the divergence theorem, section 17.8. And this is really going to bring everything together that we've been working the last few sections. So if you recall, we had in 17.4, we had Green's theorem, which talks about, see if I can point to over here, the circulation around a path can equal the double integral of the curl inside of it. And then we had the three-dimensional version of that, Stokes' theorem, the circulation around a path, if that's the edge of some surface, that can equal the integral of the curl inside that three-dimensional region. So there was also in Green's theorem, the second version was the flux form, where you can find how much flux is there across, like normal to the path. And so now we can do something similar in 3 dimensions. We could say, well, that flux across a surface should equal the integral of the divergence, like the net divergence over the region, the three-dimensional region. So the surface integral, the flux surface integral, the flow across the surface, should equal the sum of the net divergence inside of it. The only way you can get flow across the surface is to add up how much is coming out of the region. And so that is the main idea here. So if we go down to the bottom in our notes, here is the divergence theorem. So let's go ahead and fill this in. It is the double integral, the surface integral, I should say. This is the flux across that surface S. And divergence theorem says that should equal the triple integral over the region, the three-dimensional region. Let's go just a little bit. Triple integral over the region of the divergence. And so, and this is like when you add all that up, it's like the net divergence over that three-dimensional region D. So again, to summarize here, we have some key theorems we've learned. We've talked about line integrals, and if you're integrating a conservative function, a line integral of a conservative function, so it's the gradient of some phi, you can evaluate phi at b, subtract evaluating phi at a. And then we have Green's theorem. We have the circulation form, so the net circulation around the outside should equal the double integral of the curl over the inside, and then its corresponding three-dimensional version, the Stokes theorem. The circulation on the three-dimensional curve that encloses some surface, that's the boundary of that surface, should equal the integral of the curl, the three-dimensional curl over that three-dimensional region, over that surface. And then in the flux form of Green's theorem, we have the flux, the net outward flux across a curve should equal the integral of the divergence inside. And then we have the divergence theorem, the three-dimensional version of that. This doesn't really look three-dimensional, but the surface integral, the flux across that surface, should equal the three-dimensional, the integral of the divergence through the region. So we are actually going to do just 2 examples in this section. So the first one is we have a radial field, and this is a simple radial field. It's going outward. The vectors are just the components x, y, and z. And S is our old friend, the sphere, and that encloses the region. That we're going to do is a general sphere, radius a. And we're going to assume n is outward unit normal vector, and we're going to evaluate both integrals of the divergence theorem. So the first integral that we're going to do is the double integral over the surface of this f dot n ds, which is the double integral over the region once it's been parameterized of f dot tu cross tv dA, once it's been parameterized. And then the second integral we're going to do is this is from the divergence theorem, the triple integral over the three-dimensional region of the divergence. Okay, so let's take a look at this. By the way, I did get a version of this up in Maple. So, whoops, that's the second example. Here we go. So here's our sphere, and you can see that we just have vectors pointing outward. And as you get further away from the center, the vectors get longer. So they're just pointing outward out on our sphere. Okay? So that's the situation that we have here. Let's start slow. Let's actually do 2 first. So the gradient operator dot product with f will be, again, that's the partial derivative with respect to x. This is an operator vector, partial derivative with respect to y, partial derivative with respect to z, dot product with x, y, z. So that's just 1 plus 1 plus 1, right? Partial derivative with respect to x of x plus partial derivative with respect to y of y plus partial derivative with respect to z of z. So that's just 3. So all we're going to do is the triple integral over the region of 3 dv, which is just going to be 3 times the triple integral over, over the region of dv, which is just the volume. And this is a sphere. This is a sphere radius a. So that'll just be 3 times 4/3 pi times a cubed. So that'll just be 4 pi a cubed. All right? So first one, not too bad. The second one's going to be a little more work because it's a surface integral. We know we have to parameterize it. We have to find the unit, the tangent, sorry, not the unit tangent, but we have to find the tangent vectors in each direction, the u and v. We have to find a cross product. But this is our old friend, the sphere, which we have done before. So recall, I believe it's example 5. I think it's page 165, if I remember correctly. The parameterization of a sphere is basically spherical coordinates. A sine u, let me scroll down here, whoops, too far. A sine u cosine v, a sine u sine v, and a cosine u. And then we already did the cross product here, tu cross tv. That was a squared sine squared u cosine v. This was actually a ton of work at the time. So we are definitely skipping some labor here. And then a squared sine u cosine u. Okay, and then let's see, we're going to need to take the dot product of that with f. Now f equals x, y, z, but on S, on our surface, f will equal, let's see, x is a sine u cosine v. It's basically going to be our surface, right? A sine u cosine v. So the field is actually the same as the surface. A sine u sine v and a cosine u. So now we have to take the dot product of these two vectors. So we're going to multiply those together and then add those up. Multiply the x components plus multiply the y components plus multiply the z components. So that is a cubed sine cubed u cosine squared v plus a cubed sine cubed u sine squared v plus a cubed sine u cosine squared u. All right, let's do a little algebra here. Let's factor in a cubed sine cubed u out of the first two. We have cosine squared v plus sine squared v left, which is, of course, 1. Very convenient. Can we see right away? Now in the second pair, the remaining pair, not that this is gone, but this is 1, there's still an a cubed and there's a sine u in common. And check that out. When we factor that out, we get sine squared u plus cosine squared u, which is another 1. And we're left with a cubed sine u. So this is actually not too bad. We're going to have to, this was the first one, we're doing the double integral over the surface of f dot n ds. And that's equal, once you parameterize your surface, it's the double integral over the region of f on the parameterized surface, dot product with tu cross tv dA, where a is in the uv plane. Okay, so now in the uv plane, we have, oh, we forgot to do our parameters. For the entire sphere, u is, u is phi, so u is between 0 and pi, and then v was theta, so 0 to 2 pi. Okay, so double integral of a cubed sine u. All of that work, we just get a cubed sine u, not too bad. Du dv, and then u goes from 0 to pi, and v goes from 0 to 2 pi. Look at that. Beautiful, not bad at all. That's manageable, 0 to 2 pi, a cubed times negative cosine u from 0 to pi dv. I'm going to pull the negative a cubed out in front, 0 to 2 pi. Cosine of pi will be negative 1 minus cosine of 0 is 1 dv. So that'll be, what'll that be? 2a, oh, this is a cubed, 2a cubed times v from 0 to 2 pi. Look at that. 2a cubed times 2 pi, we get 4 pi a cubed. Sweet. That is exactly the same as we got, which with the much easier version. Now you'd think like integral over like a two-dimensional integral, 2D integral here over this, which is surface integral, and then you have this three-dimensional integral over the region. You think that 3 dimensions would be harder. In this case, because the first integral is actually a surface integral, the three-dimensional integral ends up being much easier, and it's kind of coincidence because the divergence is so simple, so the triple integral ends up being a lot easier. It won't always be that easy. That's fair. It won't always be that easy. So in this particular example, it was. Okay, one last example. Here we have a vector field. It's the velocity field of a fluid. And then the region that we're looking at is a solid cube. X goes from 1 to 4, y goes from 2 to 5, z goes from 1 to 4, and S is the boundary of that cube. We're going to find the flow rate of the fluid across S. So the flow rate is the flux. So the flow rate is the double integral across the surface of f dot n ds. That's the flux. Now what we're saying is, well, maybe, I shouldn't say equal to question mark. It's definitely equal, but maybe we should do the triple integral across the region of the divergence. So let me take a look. I did make this one in Maple as well. So here we have our box here, and we have like circular. If you look at it here, it seems pretty circular. Not quite a circle, but it seems to be kind of flowing around, some in and then going back out. So that is what we're looking at here. Can't really manipulate this version of it. So I think the only way to know this, we kind of know the process for this first one. This one's going to be pretty tedious, a surface integral, because we have 6 surfaces. So there's 6 sides. So you actually have to break it up into 6 integrals. So let's cross our fingers that the other one is easier, right? Please be easier. So let's find the divergence. Partial derivative of x with respect to, partial derivative of the x component with respect to x, so partial derivative with respect to x of negative y over z, plus the partial derivative with respect to y of x over z, wait a minute, plus the partial derivative of z with respect to 0, these are all 0. Oh, so the flow rate, the net flow rate, is the triple integral over the cube, the volume of the cube of 0 dv, which is just 0. Remember, if the divergence is 0, it's called source free. So what's happening here, if we click over to the Maple, I don't know if you can see, maybe we can zoom in, but what's happening is that there's the same going in as there is going back out. So there's no net flow outward, no net flow inward. It's the same, it's kind of just going right through here. So that's just the nature of this velocity field across this particular surface. So actually, no, and I take that back. That's just the nature of this field, this fluid flow field, is because it's source free. It's source free. The divergence is zero. So no matter what the region is, the divergence is zero. So no matter what region you're integrating over, the same is going to be coming in as going out. So it seems kind of anticlimactic. That's the last example. That wasn't bad at all. This video is not too long. That is it for the semester in Calc 3. The most we can expect to see from this in the future is just kind of a comparison like this, and maybe recognizing when should I do the surface integral if I'm looking for the flow rate, and maybe instead I can do the triple integral of the divergence over the region, and that is the divergence theorem.